I'm James Lawler, and you are listening to Climate Now. Today, I'm joined again by our guest host, Darren Howe, Senior Charging Manager at Cruise and former Applications Engineer at Tesla. This is the second installment of our series on decarbonizing marine transportation, and the aim of today's episode is to get a sense of the landscape when it comes to decarbonizing shipping. What are our options to reduce emissions? What are the barriers? And who are the entities that will decide and regulate how it is done?
That's right, James. For most of us, the ins and outs of the shipping industry, and why this is such a challenging sector for us to decarbonize, is not as easy for us to grasp as, say, driving or the airline industry. Luckily, we are speaking today with Dr. Bryan Comer, who leads the marine program at the International Council on Clean Transportation, or ICCT. Bryan's been researching how to assess and reduce emissions coming from marine transportation for more than a decade.
Bryan, welcome. I'd love to start with a little introduction to what the ICCT is. Can you explain to us the role of your organization and the kind of work that you do there?
Yeah, the ICCT is the International Council on Clean Transportation. We're a nonprofit research organization. And then in my role at the ICCT, I actually go and advise environmental NGO delegations at the International Maritime Organization, which makes the policy for international shipping. And so you kind of have the opportunity here to go everything from research design to doing the work to interpreting what it means for policy, and then going to explain it to the policymakers themselves on exactly what your research findings can help them do.
Yeah, out of curiosity, what is the makeup of the staff at the ICCT?
Mostly it's engineers and quite a few PhDs. Although myself and my staff, we're more on the technical policy analysis side. So we have degrees in public policy. I have a marine biologist on staff, which is kind of cool.
That's really cool that you guys have that cross-pollination going. I really want to ask what that marine biologist does on your team.
Oh, well, she has been analyzing the distribution of wash water discharges from ships that use scrubbers. So the scrubbers suck up seawater and they spray it into the exhaust, and the seawater is basic and the exhaust is acidic. And the idea is that you're removing sulfur from the exhaust to meet fuel quality standards for sulfur. So instead of removing the sulfur from the fuel, which would make the fuel more expensive, you just remove it from the exhaust. It ends up being cheaper. But then you're collecting oil and carcinogens and acids and particulate matter and dumping it into the ocean. And so she's been modeling out where do ships discharge that wash water and then linking that to impacts on marine life.
Well, I'd love to dive into our next question. Could you give us a brief overview of the shipping industry in general? So, for example, how much stuff is shipped versus manufactured locally? Maybe shipping versus freight versus rail or air.
Sure. So the shipping industry moves about 11 billion tons of stuff around the world each year. That's about 300 times more than what you move by aircraft, for instance. And those are the two main international freight transportation modes for getting across an ocean, at least. And to move 11 billion tons of cargo, ships are emitting about 1 billion tons of carbon dioxide. And if it were a country, the shipping sector would rank 6, more than Germany.
To put those 11 billion tons in context, what percentage of that is that globally?
Let's see. Well, yeah, it's about 80% of total freight transportation by mass is carried by ship. A lot of people say 90%. It's actually more like 80%. And that's about 70% by value.
Gotcha. Thanks for that context there. Now, we're obviously not shipping experts, so can you enlighten us on the types of ships there are, what they transport, and then maybe how shipping emissions are distributed among those different types of carriers?
In my team, we like to say that there's the big three, and those are container ships, bulk carriers, and oil tankers. Those three ships account for over half of the emissions from the sector. There's about 50 to 60,000 commercial ships that are big enough to really count. In total, around the world, there's hundreds of thousands of ships, but you have to sort of draw the line somewhere. So of those 50 to 60,000 ships, 5,000 are container ships, so about 10-ish% of the fleet. And they're responsible for about 25% of carbon dioxide emissions from the sector. And then we have bulk carriers. There's about 10,000 of those, and they are responsible for about a fifth of emissions, and then oil tankers for about a sixth of emissions. So the container ships are moving manufactured goods back and forth. If you look around your office and look at all the stuff you have, quite a bit of it, maybe all of it, was moved at some point on a ship. But the other portion of the shipping industry that maybe doesn't get as much attention is just how much fossil fuels are transported by ships. So we have bulk carriers and oil tankers, and those two are transporting coal and crude oil and petroleum products, diesel fuel, and about 40% of that 11 billion tons of cargo that's moved is fossil fuels.
Wow. So 40% of the cargo we are moving around in these carriers and tankers are fossil fuels. So just reducing our dependence on fossil fuels in all other sectors would have a huge impact on reducing shipping emissions. But let's get into some specifics. What are the actual goals for emissions reduction in the shipping industry itself?
So the shipping industry is regulated by the International Maritime Organization. It's a specialized agency of the United Nations, and it's designed such that countries that are interested in shipping, which is almost every country on Earth, come together and put together proposals on how to regulate ships for safety and for the environment. So the International Maritime Organization, 2018, we agreed to a couple of targets. The first is that by 2050, absolute emissions from the sector would fall at least 50% from 2008, which was the historic peak in shipping emissions just before the global financial crisis. And by 2030, we would reduce the carbon intensity of shipping, so how much carbon dioxide or greenhouse gases are emitted per ton nautical mile, by at least 40% compared to the 2008 baseline, and that we would work to eliminate greenhouse gases from the sector as soon as possible before the end of the century, and that we would try and align the strategy with the Paris Agreement temperature goals, maybe more than try. The vision of the strategy is to be aligned with the Paris Agreement temperature goals. So you may intuit that a 50% reduction by 2050 is probably not aligned with the Paris Agreement temperature goals. So part of the initial strategy is that it's reviewed and updated every 5 years. So in 2023, next year, we're going to have the first revision of the greenhouse gas strategy. And the United States, under the Biden administration, has put forward a proposal with other countries to achieve zero emissions by 2050, not even net zero, literally zero emissions from the sector by 2050. And other countries have come on board with proposals for net zero by 2050, recognizing that you might need to use sustainable biofuels or synthetic fuels made with renewable electricity that have negative upstream emissions when you produce them and positive downstream emissions when you burn them in the ship. So the actual targets for the sector are expected to really strengthen next year, but there's a big mismatch between ambition and the regulations that the International Maritime Organization is developing to actually try and achieve those targets.
What are the actual strategies that are proposed in that target? Like what is the path to get from where we are to zero emissions by 2050?
So there's, at the International Maritime Organization, usually the debate goes like this. What's the target? Let's negotiate that. What numbers sound good? What years sound good? From what baseline? Okay, then how are we going to achieve this? But the negotiation starts first on what are the targets? And then how do we get there?
Is it just like finger in the air, this target sounds good? Or like how does that initial stake in the ground get set?
My group tries to explain, if you're trying to be aligned with the Paris Agreement, what's the emissions reduction trajectory that you need to be on in order to have a carbon budget by 2050 that could be consistent with the Paris Agreement temperature goals. Basically, how much carbon budget do we have between now and before we exceed 1.5 or 2 degrees? And then what does that imply for how quickly we need to reduce emissions from the sector? And then in addition to that trajectory, we model out how much can you achieve just by operational measures. The easiest thing to do is to slow a ship down. There's a cubic relationship between how fast you go and how much fuel you consume. So in order to go just a little bit faster, you have to consume a lot more fuel. And the opposite is also true. If you go a little slower, you consume a lot less fuel. Even though it'll take you a little longer to complete your journey, because it's a cubic relationship, you end up saving fuel. That's the easiest thing to do.
You know, I'd love to ask you a question about that James Womack and Daniel Jones describe the creation of a tin can in their book, Lean Thinking. First, you have bauxite, which is the raw ore from aluminum, which is mined in Australia. That is reduced in a chemical reaction and shipped as aluminum oxide to Sweden or Norway from Australia. In Sweden or Norway, it sits in a yard, sometimes for several months, before it's processed into aluminum ingots, which are then shipped to Germany, where it sits for a number of weeks before it's rolled and flattened, and then sent to England, where the cans are actually made. And so at each step, you've got huge amounts of emissions that are released from the heat required for that step of the transformation. And at each step, you have transportation, punctuated by a lot of waiting around. It's a great case study for just how inefficient the whole system ends up being. And I'm wondering if that, resonates with the work you've done.
It does. That is one interesting challenge of the international shipping industry, is how do you make sure that the ships that are arriving at ports are doing so at a time that makes sense to reduce congestion, to make sure ships aren't just idling off the coast, which is a big problem that we've had during the pandemic off the West Coast with container ships and with oil tankers actually as well. But there's not a global logistics plan to make sure that all the ships are operating in harmony across the seas. And so slowing the ship down could reduce congestion, because you would have more time to figure out when the ship ought to be calling at the port. And then also it could be a lot more efficient. There's likely some interaction here between the speed at which the goods need to get there and how the ship is rented out. So the bulk carriers and the oil tankers, they're rented out. So they're chartered is how we would call it. And so whoever's renting the ship tells the ship when it needs to leave one port and when it needs to arrive in the other port. And then the captain of the ship is in charge of figuring out what speed they should sail to get there. And you don't want to miss that window. There's fines associated with that in the charter agreement. And so there is also this hurry up and wait that can happen in the industry because of how the charter agreements are working out.
I'd also love to ask some other questions around, what makes it difficult to accomplish these goals that you mentioned, right? Are there nuances that most people don't think about that make it difficult to say one thing but actually achieve that goal in the maritime industry?
There's a couple of challenges. One is on the policy side, and the other is on the economic side. So the only way we're going to reduce emissions from the shipping sector is either if we make regulations that mandate that ships do something different than they are currently doing, or if it's less expensive to do the right thing. And on the policy side, the International Maritime Organization usually ends up with regulations that are the lowest common denominator, because they're trying to work under consensus, not necessarily unanimity, but you'll have countries that are quite ambitious, and you'll have countries that want to maintain the status quo or even move backwards. And you end up with a regulation somewhere in the middle that usually is only an incremental improvement on where the industry was headed already. That needs to change if we're going to achieve zero emissions by 2050 for sure. So that's one challenge. The other challenge is it's a global industry and competition can be fierce. And so whoever is offering the cheapest way to move whatever you're trying to ship from point A to point B, that's who wins. I mean, the option now to run a ship the cheapest is to flag in a country that isn't going to charge you any extra taxes, is going to have lax environmental and safety and labor standards, and is going to allow the ship to use the cheapest fossil fuel. And in fact, we have a situation now where in 2020, the fuel sulfur limit for marine fuels reduced from a maximum of 3.5% to 0.5%. And that was supposed to have this shift to more expensive fuel, which would encourage ships to slow down and reduce their emissions. But what ended up happening instead is that a lot of ships installed sulfur scrubbers so that way they could keep using the cheapest high sulfur fuel and keep their freight rates low. So the economics is really a challenge. Until the alternative fuels are less expensive than the fossil fuels, then nothing's going to happen on the market side. So we're working from a market angle and from a regulatory angle all at the same time and trying to pull enough levers on both of those sides to make sure that we actually do start reducing emissions from the sector, because so far between 2012 and 2018, we saw a 10% increase in emissions. So we're going the wrong way.
Got it. Well, this is a great segue to start talking about some of the solutions that you've seen. Could you tell us about the trends in shipping decarbonization? What are some of the technologies or leaders in the space?
Sure. So there's a lot that we can do on the operational side, which I mentioned earlier, including just slowing ships down. But in order to get to zero emissions, we need to change the way that ships are fueled. And that's requiring a change not only in the type of fuel that's used on board ships, but also the type of propulsion system that we have on board the ships.
And could you just walk us through what those different options are in making those changes?
Right. So when we're thinking about the fuels that could be used to power international shipping, you need something that has a good energy density and that's not too difficult to handle, and that you can use either in an internal combustion engine or maybe a fuel cell. And so if we start with maybe the hardest situation, which would be a liquid hydrogen fuel in combination with a fuel cell, that requires having very insulated tanks, very cold fuel, and running it in a fuel cell, which hasn't been tested at scale yet for international shipping. And then it gets easier from there if you go to ammonia, which you can use in an internal combustion engine that is easy to be liquefied. It's a gas, but if you apply just a little bit of pressure, it'll liquefy, or if you cool it down just a little bit, it'll liquefy. So it might as well be a liquid. But burning it, you're going to produce nitrous oxide emissions, N2O, and that's a greenhouse gas with a global warming potential almost 300 times as strong as carbon dioxide. And we don't know how much will be emitted by burning ammonia in a marine engine. So it's not going to be zero greenhouse gas like using hydrogen in a fuel cell would be. So then we're talking about methanol. Methanol is a liquid at room temperature and pressure. That's good. We can store it on board the ship. It's got about half the energy density of fossil fuels. So you need twice as much of it if you're going to go the same distance. But the same is true for ammonia as well. It is a hydrocarbon fuel. So when you burn it, you're going to produce carbon dioxide. So the source of the carbon is really critical when you're using methanol as a decarbonization strategy. And we have biofuels and we have synthetic fuels as our options. There's huge concerns on the sustainability of biofuels because many of them are made with corn or soybeans, and those have direct and indirect land use change consequences that can make them worse than fossil fuels that they're replacing. If it's from a sustainable biosource, that like something that would have become a waste material, then that's good. But the supply of that is really limited. If it's from direct air capture of carbon dioxide, that's good. You can call that net zero carbon dioxide. But that's where the challenges of cost and scaling up come into play. But we are seeing companies like Maersk, who have been the leader on the container shipping side and really for the international shipping sector in total, starting to invest in companies that actually produce green methanol. And they're being transparent, or they intend to be transparent at least, about what the source of the carbon dioxide is and how they're doing the conversion. So we're looking to hold them to account on that and make sure that they're transparent.
So Bryan, I noticed you didn't include liquefied natural gas or LNG on your list of options, even though I understand it's being touted as a way to quickly decrease shipping emissions. Can you comment on why it didn't make the list?
No, we actually didn't talk about LNG at all, which is one of my hobby horses on why it's not a climate solution for ships. And yet half of cruise ship capacity that's being built today, and I think it's a third of container ships and maybe a quarter of bulk carriers and oil tankers are designed to run on LNG, which is methane and burned in engines that are leaking large amounts of unburned methane to the atmosphere. And we're actually just launching a study. We launched it a couple of days ago called Fumes, Fugitive Methane Emissions from Ships, where we're partnering with a company that flies drones and helicopters and another research organization that goes on board ships to actually measure methane emissions from LNG fueled ships to try and better understand the greenhouse gas consequences of using this fuel that has lower carbon dioxide emissions, but higher total greenhouse gas emissions in most cases.
That's a good point, that all these fossil fuel alternatives might reduce CO2 emissions, but they come with other risks. For example, I know with ammonia, one of the big challenges is the safety of this toxic material. Maybe you could speak to that a little bit more. And on the methanol side, correct me if I'm wrong, but I've heard that methanol can actually corrode steel, and that will make it more difficult to adapt traditional containers and pipes to handle that fuel.
So methanol is already transported by ship. And so there's actually been a lot of work done ensuring that the methanol can be safely handled on board ships. And it was just approved, I think it was last year, as a ship fuel. So on the safety side, IMO's actually pretty competent on that. So that I'm not too worried about. It is toxic though. You don't want to ingest it, but it's not a breathing hazard like ammonia is. So if there's even a small ammonia leak, then the entire crew could be killed. Or if there's a spill, then the marine life would be killed as well. That's around the ship. So there's
biologists would not be very happy with that.
Yes, our marine biologists would not be happy with that. So that's a big challenge. Methanol, if it's spilled, it is biodegradable, but there's some acute toxic impacts as well during the initial part. So I mean, there's trade-offs with all of this. I think the safest thing would be green hydrogen. Even that's not risk-free because you have a fire and explosion hazard, but if you're going to have a fuel on board the ship, unless it's wind power, then all of it needs to burn. So, but that has the advantage of not being toxic, not being poisonous, and not being a greenhouse gas.
Yeah, let's talk about hydrogen to wrap this up, actually, because one of your papers mentioned that you studied, I think, a trans-Pacific corridor route, and you found that 99% of those voyages could actually be powered by cryogenic liquid hydrogen and not really affect the fuel capacity or operations very much. Can you maybe speak a little bit more to that? Why are we not hearing more discussion of cryogenic hydrogen and fuel cells in that case?
So we modeled out the Trans-Pacific container ship corridor, and we looked to see if you could complete those voyages using liquid hydrogen fuel, which is cryogenic, by fitting it within the same space as the existing fuel tanks and the engine systems and not changing the speed of the ship or anything like that. Half of the voyages could be achieved just as they normally were. You didn't have to change anything about it. The other half, you would need to add an additional refueling stop to complete the voyages. And in that case, you could achieve 99%. The other way to achieve it is you replace some of your cargo space with fuel, but it's not necessary if you have that additional refueling stop. And we've also modeled out pairing hydrogen fueled ships with wind assisted propulsion, which reduces how much fuel you need to consume because you get power from the rotor sails, in this case, is what we modeled.
Gotcha. So I was probably being a little optimistic and saying barely any changes. There would have to be refueling stops or minor changes to cargo capacity.
The one thing that we didn't model out, though, is what if you slow down the ship a little bit? And in that case, almost certainly you would be able to achieve all of the routes with a reduction in speed. But we wanted to do a pretty tough scenario because we knew that everything else would be easier.
Have you ever done an analysis of what would happen if you pulled all the levers or looked at which of these strategies will have the biggest and fastest impact and where we should be concentrating our efforts? Because it strikes me from our conversation that slowing down is going to give us the biggest bang for our buck.
Well, I mean, we've definitely modeled out how exactly you could get to zero emissions on a trajectory that could be consistent with the Paris Agreement temperature goals. And it requires slowing down as the first step. And then it requires scaling up the low and zero life cycle greenhouse gas fuels pretty rapidly. And that would require reducing all of the political and economic barriers to progress. So it's certainly possible. It's definitely possible. The challenge here is going to be to do it in good time and make sure that we have rules that are in place that force the transition to occur, and not just things that rely on the market to incentivize the change. We need a combination not only of the market-based measures, but also command and control.
Well, Bryan, thank you so much for your time today. This has been really fascinating, and we've covered, it's a great primer really for anyone who's interested in this space.
Yeah, thanks for joining us, Bryan. This was really fascinating.
My pleasure. Thanks for having me, and thanks for your interest in our work.
That's all for this episode of the podcast. Climate Now is made possible in part by our science partners like the Livermore Lab Foundation. The Livermore Lab Foundation supports climate research and carbon cleanup initiatives at the Lawrence Livermore National Lab, which is a Department of Energy applied science and research facility. More information on the Foundation's climate work can be found at livermorelabfoundation.org. To listen to other interviews from Climate Now, watch our videos, read our articles, or sign up for our newsletter, visit climatenow.com. If you'd like to get in touch, you can email us at contact@climatenow.com or tweet us at @WeAreClimateNow. We hope you'll join us for our next conversation.